All right, so today we're going to be starting a new unit with the first page of the lilac colored notes. And this new unit is going to deal with the atmosphere, which is one of the spheres of the Earth. But before we focus on the atmosphere, let's look at these other layers of the Earth. The hydrosphere is the liquid water portion of the Earth. So basically the ocean, right? Now when the Earth first formed, it did not have an ocean. So where did the water come from? A few places. One, from when it's been raining for millions and millions and millions of years. And or you might wonder, where did the water come from to make the clouds then? Largely from volcanic eruptions. When volcanoes erupt, it's not just lava that comes out, there's gases that come out too. So that's where atmosphere comes from. And you get the water, and then when it rains over millions and millions of years, they can help build up the ocean. Also, from comets. If you remember what a comet's basically a big dirty snowball, big chunk of ice. So when the Earth gets hit by a comet, it deposits a bunch of water at the Earth's surface. So it's a combination of these things that scientists think is what created the ocean. Right? But we'll look at the hydrosphere. Actually, in the next topic, we look at water in a lot more detail. The lithosphere is the rock layer of the Earth. The top part of that is called the crust, and we deal with rocks more so a couple months from now. We'll look at rocks. Pretty much from then to the end of the year, we'll look at rocks in more detail. So the hydrosphere is the water part, the lithosphere is the rock part, which brings us to the part that we're focusing on today is the atmosphere, which is the shell of gases surrounding the entire Earth. All right, so there's no place on the Earth that is not covered by the atmosphere. Even if you climb up to the top of Mount Everest, you're still covered by the atmosphere. The atmosphere's gonna be a little bit thinner up there, but you're still covered by the atmosphere. Now, the atmosphere is broken down into a few different layers. And we'll look at a chart that shows us those layers in a little bit. The bottom layer, the layer that we live in, is referred to as the troposphere. So the troposphere is the bottom layer of the atmosphere. And the reason why we have different layers of the atmosphere is the properties or characteristics of each layer is distinct from the other layers. So again, we're going to look at what these varying properties are and what these layers are in a little bit. Now, when the Earth first formed, it did not have an atmosphere. When the Earth first formed, it's basically like the surface of the moon. So where does the atmosphere come from? The Earth's early atmosphere formed as a result of outgassing of water vapor, carbon dioxide, nitrogen, etc. from the Earth's interior, often during volcanic activity. So when volcanoes erupt, it's not just lava that comes out of the volcanoes. There's gases that kind of bubble up through the lava as well. And if you go back like 4 billion years ago, there was much, much, much more volcanic activity than there is today. The volcanoes erupted far more frequently than they do today. So there was lots and lots of gases being spewed out from the inside of the volcanoes, from the inside of the Earth, that gets released to the surface, and then the Earth's gravity kind of holds those gases to the surface, and that's where our atmosphere initially comes from. Right? Now, the composition of our atmosphere is changed over time, and if you look at here, one really important gas that you do not see there is oxygen. The Earth's early atmosphere did not have any oxygen in it. So if I was this really smart guy and I built a time travel machine and went back 3 billion years, as soon as I walked out of my time travel machine, I would suffocate because there wouldn't be any oxygen to breathe. The oxygen came later, and where the oxygen came from is from life. One of the first creatures that developed on the Earth was algae, right? Algae is basically a very simple plant, right? It has chlorophyll, it carries on photosynthesis. Now, if you remember what happens during photosynthesis, photosynthesis takes carbon dioxide and water vapor and sunlight, and then turns that into food and oxygen. So the oxygen is like a waste product of photosynthesis. So you have all these little algae in the ocean, and they're releasing all these little bubbles of oxygen, which kind of come up through the water and get released to the Earth's surface. And after millions and millions and billions of years, the oxygen builds up to what we have today. Now, again, the concentrations of these gases has changed throughout time. Right now, we're at about 21% oxygen, but if you go back to the time of the dinosaurs, the oxygen was actually higher than it is today. Back at the time of the dinosaurs, the oxygen was around 30%. The significance of that is that the more oxygen there is, the bigger the creatures could get. That's one of the reasons why creatures were so big back then. You had like dragonflies with 6-foot wingspans and millipedes that were like 6 feet long. Because there was such a high oxygen concentration in the air that allowed the creatures to grow a lot bigger. We're at about 21% now. Yeah. Now, so the percentages of some of these gases can vary. And even today, our atmosphere is changing. Today, it's largely the result of human activity, though. So human technology is currently what's responsible for changing the atmosphere. Now, there's several examples of this I could bring up. I could bring up adding of CFCs or chlorofluorocarbons, eating away at the Earth's ozone, and there's a few other things that I can mention as well. But the one we're going to focus on is the carbon dioxide. All right. Combustion, burning things, and I say things, I mean things like wood, coal, oil, paper, things like that. Combustion, burning things, produces carbon dioxide. All right? Now, people have been burning things for thousands upon thousands of years, burning wood to stay warm and stuff like that. But up until recently, up until the last couple hundred years or so, it's been a really small amount, just basically to heat yourself so you don't freeze to death. But a little over 100 years ago, there's a couple inventions that increased dramatically the amount of fossil fuels and stuff that we use. One was the invention of the internal combustion engine, late 1800s, where you could burn like gasoline and stuff like that, and make something turn. All right, that's what's in the type of motor. It's in a car or old-time airplane, things like that. So over the last 100 years or so, as more people in the world have more money and buy more cars, and there's more roads, which makes more cars more feasible and so forth. The amount of cars has increased dramatically. Well, cars burn gasoline and release carbon dioxide, so the amount of carbon dioxide levels has gone up dramatically as a result as well. Another thing that happened in the late 1800s was basically the invention of the light bulb. Once they had like a light bulb that could stay for a long time, what would happen is because back in like the 1850s, if it was dark in your house, you had a little lamp, right, like an oil lamp or something like that. But once you got the light bulb, what would happen is people would have electric lights in their house. They'd have to run electric lines to their houses for the lights. Well, once you have electric lines in your houses for the lights, then it's like, well, wait a minute, I could use this electricity to turn a fan. I could use this electricity to listen to the radio. I could use this electricity to for a refrigerator and so forth. As a result, people have more and more things that are based on electricity. And where does electricity come from? The electricity comes from power plants, many of which are based on coal or gas. So you burn lots of coal and gas, and it makes electricity, but you're also spewing a lot of carbon dioxide into the atmosphere as well. Now, over the past 100 years, every single year, the amount of carbon dioxide has gone up. And again, it's largely the result of those two things. Coal burning electric power plants and lots of cars. Yeah. Now, there's a couple charts in your reference tables I want to show you. All right, so this chart here is on the front page of your reference tables, and it shows you the compositions of the various layers of the Earth. So the hydrosphere is the water layer of the Earth, the crust is part of the lithosphere, and the troposphere is the bottom layer of the atmosphere. So it's the layer that we live in. So it shows you which elements make them up. So the hydrosphere, I can see, is 66% hydrogen, 33% oxygen. Well, that makes sense because water is H2O, 2 parts hydrogen, 1 part oxygen. All right. The crust has it broken down by mass and by volume because there's some elements that might be very small, but they might be very dense, and they might have big masses but small sizes. So they have it done both ways. But what you should notice here is that just these top 8 elements here really make up most of the elements that you experience outside. So if you pick up a rock, most rocks are going to be composed of these 8 elements right here, because if you add those up, it works up to be like a high 90%. So it has by mass and by volume. So you can see that silicon and oxygen are really the 2 biggest elements for rocks and so forth in the Earth's crust. The troposphere, part of the atmosphere that we live in, I can see that 21% of that on average is oxygen, 78% of that is nitrogen. All the other gases combined are only about 1%. Now, you should know that we need oxygen to survive. The nitrogen really doesn't do anything for us. When you breathe, about 3/4 of that air, your lungs are just pushing around stuff to get to the oxygen. So the nitrogen you breathe in, nitrogen you breathe out, your body doesn't do anything with it. All right, so there's one chart I want to show you. The other chart I want to show you goes with is on page 13 of your reference tables. This chart right here. And this chart here shows you the various names, the various layers. The troposphere, stratosphere, mesosphere, thermosphere are the various layers of the atmosphere. Here it shows you how high they are above sea level. So it has one side of it has in kilometers above sea level. The other side it has it in miles above sea level. Right. Now, the various layers of the atmosphere, the troposphere, stratosphere, mesosphere, thermosphere. The tropopause is not a layer of the atmosphere, it's a boundary between layers. The word pause means to stop, like if you word pause on a DVD player or something, it stops it. So what that word means is if I'm going up through the troposphere, the tropopause is where the troposphere stops and the stratosphere begins. So I'm traveling through the stratosphere, and the stratopause is where the stratosphere stops. And then I enter through the mesosphere, and the mesopause is the point at which the mesosphere stops and the thermosphere begins. Right. This line here shows you what happens at temperature. So I can see at sea level, on average, it's about 15 degrees Celsius. As I go up, the temperature decreases as I go through the troposphere. But then once I enter the stratosphere, the temperature goes up. And then when I get to the mesosphere, it goes back down. And then in the thermosphere, it goes back up again. What pressure is? Air pressure, atmospheric pressure, is the weight of the air on top of you. So for example, if there's like a little dude right there, all this air above him is pressing down on him. All that air above him is pressing down on him. It has a certain weight. Just like if you're going swimming in a swimming pool, when you go farther down, you can feel the pressure of the water pressing on your ears. The farther down you go, the more pressure you can feel on your ears. That's because the farther down you go, the more water there is pressing on you. Well, the exact same thing holds true the atmosphere. If I'm higher in elevation, all right, there's less air above me pressing down on me. So this guy would have less air pressure here because there's less air pressing on him. This guy down here, he has a much larger column of air pressing down on him So he's going to feel more air pressure. So the higher up you go, the less air pressure there is. And that's basically what this is showing you, is that at sea level, right, the atmospheric pressure is 1. And then as I go up, it goes to 0.75, 0.5, 0.25. So as I'm going up in elevation, this line is getting closer and closer and closer to 0. Because the higher up I go, the less and less air pressure there is, because there's less air above you. The last thing I'll show you on this chart is the water vapor content. So at sea level, on average, it's about 25 grams per cubic meter. But as I go up, I can see it goes to 20, 15, 10, 5, like 2. Virtually all the water is down here in the troposphere, all right? There's a tiny amount of water in the stratosphere, but just towards the bottom of the stratosphere. Most of the water is down here in the troposphere. The significance of that? Well, that's where all the weather happens. That's where you're gonna get clouds and rain and so forth, is down here. You don't get little clouds and stuff up here because there's no water up there. So virtually all the water is down here in the troposphere, all right? So that is the atmosphere chart.